general covariance is a constraint on solutions. Okay, so I have an entire script here to read, but I'm a few beers in, and the entire point of this is to explain the proposal off the cuff. And the idea is very, very simple. It's very simple. I don't even know if I should bury the lead or not. But the idea is basically that the postulates set forth in general relativity, everything that is actually composed or created or derived, however you want to describe it, everything within general relativity, if you dissect it exactly the way it is described, you can obtain a cosmological solution. It's a global solution. And in this video, I'm going to try my best to present this argument as cleanly as I possibly can. But I'm going ad lib. I'm going off the cuff. I'm just talking off the script. I have an outline to follow, but that's probably going to get discarded in just a second. Unfortunately, at this point, I've had 6 Wicked Weed Freak Nature Imperial IPA beers, and they're about, 8% each, so they're pretty potent beers. And so my speech may be a little slurred. I'm doing the best I can. This is actually what it takes to do cutting-edge science. You have to get drunk. I mean, that's the truth. I've spent No, that is not true. I don't even know why. I've spent countless hours thinking about how to get a paper past review or into review. You got to get it past the editor. In science, they may just place some astronomer that has 10,000 articles published. But those articles are all from observations. They're not theoretical science. In theoretical science, in order to publish a paper, you have to have already published a paper and have a recognizable name. That is the standard that reviewers go by. It is not the arguments presented in the paper. They don't even read the paper. Their decision is whether or not to send it to review. They don't want to send anything to review that is cranky. And obviously, anything that someone like me is going to write is going to be cranky. You can try to disguise it if you'd like. I don't like to do that. To me, present the arguments and go through them. That's what we're going to do tonight. We've only wasted 3 minutes so far. We're 3 minutes in, and you kind of have an understanding of what I want to do tonight. Tonight, I want to present my arguments in the most purest possible form. And if you can follow those and engage with those arguments, you will understand that the majority, the lion's share of mysteries in physics can be resolved by just simply reading Einstein's words. Now, of course, this is an outrageous claim. It's outrageous. But I want you to think on something for a second. I'm going to give you a statement, and I want you to think about it heavily for a moment. Now, you have to reflect on this. You can't just dismiss it, okay? Promise me that you are going to reflect on this. The main postulates of general relativity, in other words, you have general covariance, diffeomorphism invariance, and then you also have a unified metric. The unified metric is the ideal metric. It is the metric that describes the entire universe, okay? This is the metric. That metric is what we're all trying to mimic when we produce solutions to the field equations. We have never actually produced that metric. I don't know what you want to call this metric. It is the global metric. It is the unified manifold. It is the thing that we're inside. It is the universe. Okay? Hopefully you agree with me kind of somewhat so far. Is the idea that Einstein presented this idea that there's this manifold that exists, and these field equations are always satisfied in this manifold, and that we exist inside of this manifold, okay, this metric. This metric is a mathematical structure. That's all it is. It's a bookkeeping device for the global metric, for the universe. The universe has a built-in bookkeeping device, and it's relational. Hopefully, we're all on the same page, because I've not made any superficial claims or claims outside that of those that are objectively known in the consensus of science. However, we can take this a step further. There is a hidden thing within this global metric, or global manifold, or unified manifold. Whatever the thing is that Einstein's describing, there is an underlying structure to this, and the reason is because there is a uniform constant that is imposed on us. This uniform constant is called surface density. And the reason that surface density is imposed on us is because it must be so for the relationships involved to work. And that is because volume is different than surface area. And this is very, very esoteric, and this is very, very difficult to follow if you're not accustomed to Einstein's general theory of relativity on a very personal level. If you've never engaged with Einstein's general theory of relativity, you're going to have no idea what I'm talking about. There's not much I can do about that. But the idea in general theory of relativity is that there is a unified metric. So this metric is kind of like a Cartesian coordinate system. It's a bookkeeping device. That is all. So the idea is that there is a bookkeeping device that maintains track of everything. And it does this through the relational properties of all of the things. I know this is crazy. If you're not aware, or if you're not into the general theory of relativity, then this is going to be nonsense to you. I can't help that. But the idea is that there is this unified manifold. Unified manifold. It's a unified metric. And by unified, I just mean that there is no stitching required. And by there is no stitching required, I mean that you can calculate anything holistically. You don't need to limit your algebra in any way. You don't need to make any assumptions. You don't need to make You don't need to draw any boundaries. You don't need to do anything. That everything about the metric is actually contained within the metric itself and the assumptions thereof. So you don't have to do anything. All you have to do is assign a scale, and then the scale will determine all of your values. So that is the idea of a global metric. I may not be doing a good job of explaining it. I'm doing the best job I can of explaining it. So in general relativity is proposing that the universe is this mathematical structure. And there's something called the general covariance, or it's the the principle of general covariance. And the idea of general covariance is that the forms of all physical equations stay the same in all coordinate systems. Because in general relativity, the coordinate system is heavily observer dependent. It's conditional. So you can describe your metric and it can satisfy the Einstein field equations. But it may not necessarily be the metric. It's only the metric for your limited domain, whatever conditions you applied to your metric. But in the general theory of relativity, there is a proposed metric, a manifold, a unified manifold, the unified manifold, and any existing or any proposed metric solution would actually fit inside of the unified manifold. And I'm sorry for the way that I'm enunciating things. It's my task is extremely difficult, and I'm doing this the most intuitive way possible. It may be socially irresponsible or weird or whatever, but I'm doing the best. I'm doing the best way that I can to explain it. It's very, very abstract, but it's also extremely simple. Let's pause and review. I am making no claims thus far. Thus far, my only claim is that general relativity has a global metric. And this global metric is actually what determines the universe. That our solutions, the exact solutions or proposed solutions or conditional solutions, all of these things that scientists have prepared and submitted over time, i.e. Kerr and Schwarzschild, all of these types of solutions, they are shortcuts. They are approximations to the global metric. And so the idea is you can create a metric for a star, say the sun. You can use the properties of the sun to create a metric that will locally align with the metric of the sun. And then you can make predictions about Mercury or whatever you would like. And those are accurate, but they're only accurate within that very specific domain. That's because they don't include the rest of the universe. And so the idea is that you can take all of these local solutions, stuff like the Schwarzschild metric, the Kerr metric, the FLRW. The FLRW is a little different, but there's a whole bunch of exact solutions that are known. And the idea is that if we actually could tweak these just a tiny bit to where they're specific, then we could create a global metric that actually accounts for all physical phenomenon. But it would be difficult, don't get me wrong, but the idea is that it's technically accurate. We're just kind of leaving some information on the table by making these assumptions. That entire framework is fine. There's nothing wrong with that. That is not... The purpose of this video is not to discredit that practice. That practice is amazing. That is actually the intent of general relativity, is you create a solution the best you can to describe the situation you're discussing. That's because mass and energy and everything is relational. All of the relationships are relational. And it's difficult to discuss. So that's why these solutions like the Schwarzschild metric, they are definitely positive impacts on science. That is not the claim of this video. This video's claim is that there is a single global metric that can be derived from the basic principles of general theory of relativity. And that metric is a cosmological metric. We'll get to this. I'm going to go into more detail. I don't know. I'm trying to think about where you may be confused at this point. And there are numerous places that you could be confused depending on your knowledge and experience within general relativity. But the idea is very, very, very simple. We're 16 minutes in, and I'm just now getting to the idea. Surface density is uniform, and it must be uniform even within the general metric, the global metric within general relativity. Surface density is always going to be a constant. If it's not a constant, you're missing information. If your metric doesn't contain a constant surface density, then you're limiting the algebra in some way. I would urge you to read the page curves. I don't remember the exact title. It's something to do with, just Google page curves and entanglement islands. You'll get it. It'll be first result. Anyways, there's a new paper in the archive, and it explains how limiting the algebra in general relativity is always going to produce some bullshit. What I mean by that is that you can't just come up with an idealized solution for an idealized scenario and expect the algebra to completely work out in the global solution. And we would hope the entire point of general relativity is that there is a global solution. You know, some people think that it's not presentable as a mathematical solution. That's fine. That's fine. I just need people to agree that there is a global solution. And that's not my proposal. That's Einstein's proposal. The idea is that it's a unified manifold. That means it's a global solution. That's the entire point of modern cosmology. That's the entire point of the Friedman, Lemaitre, Robertson-Walker metric, the FLRW. That's the entire point. The entire point is to come up with this unified global manifold. Now, the thing is physically and mathematically speaking, if you don't have any boundaries, then the surface density is a constant. Now, you're going to have to reflect on that. You can't just hear that and then dismiss it immediately. Surface density must be a constant if there are no boundaries on your manifold. And the reason is because there's only one possible partition. If there are no boundaries, there's only one possible partition that allows you to inspect a slice of the radial coordinate. I know this sounds so stupid, but the slice of a radial coordinate, or I don't even know the exact way of explaining it, but if you slice it up to inspect it, okay, your slice is going to have a width that is the same as your partition. The only possible partition is a cosmological horizon. Now, the papers that I'm writing are a lot more specific. Every time I make a statement in when I'm recording audio like this, every time I make a statement, I think about all these qualifying things that I've got to say. And that's the problem with using plain language. And that's what makes physics difficult, is that you have to make everything extremely precise. But the idea is simply this: the global manifold, the unified manifold, if it is boundaryless, then the surface density is a constant. And this, from that information alone, you can construct a global metric that doesn't need a bunch of stitching or assumptions or boundary conditions or anything that's imposed by humans. You simply derive this metric from the unified manifold. See, it's extremely esoteric and abstract. I don't even know what the best way to explain this is. I'm still working through it all. But this argument is incredible because I'm able to derive the metric that I've created from all of my previous research. I'm not making any assumptions. My only assumption is that general relativity is true and the postulates of general relativity are true. And if I make those assumptions, then I am left to ascertain that surface density is a constant. And by constant, I don't really mean it's a constant. It's a geometrical scale. It's a relationally dependent geometrical scale.